Experimentalism is a key facet of any quality science education, but not all schools are equal in terms of facilities, laboratory equipment, and so on. But try not to let that stop you. Every school has an old storeroom where they often keep equipment that has been built up over the years. Let's visit our local storeroom and see what we can find. Here's what I was looking for. Pulleys. And there's all kinds here. Some of these are really a cheap plastic. Others are old, but these are still of high quality. And there's even a few metal ones in here. These pulleys are a gateway to entering into experimentalism. People think pulleys are magic, and students have all kinds of misconceptions about these. Either way, they're going to be interested. So let's start setting these up. If you have the luxury of having a large lab, you can set up each table as a separate set of pulleys. Here I've got 2 pulleys on top, 2 pulleys on bottom. I've got a nice bar set up. And of course, put foam down in case anything goes wrong. These can unwind. But if you don't have the space to do 1 table per set of pulleys, there's other ways to do that. Let me show you. Walk around your building or classroom, maybe check closets, storerooms. Find hooks or something that's coming out of the ceiling that you can hang things off of. If you can't find hooks, you can often put a metal bar between them and hang numerous pieces off here. If you can't find a way to hang things from the ceiling, that's okay. Sometimes you can find these universal rods and clamps. This one's already together. Simply put them on the side of a desk or a table. This is a demonstration table that you can have on wheels. Many schools will have one of these that you can wheel from classroom to classroom. Once you get 2 vertical poles, you can tape or really do anything that you need to get a hanging apparatus. This is from a previous video that we did, and I just drilled some holes of the same size as these rods, and then I can just pop that one in, and I can move this over and pop this one in here also. And while it's not perfect, it'll do. I can hang some of these pulleys that I was talking about over top here. And if I don't want these, I can always just take a meter stick and then tape these together and then hang things from a meter stick. Nothing else, go talk to your shop teacher. You're bound to find something that you can hang a few pulleys off of. Once you do that, then we can begin. Here's a couple of those plastic pulleys that I showed earlier. They're not perfect, but they'll work. And what do pulleys do? Well, pulleys help change direction. So for today, we want to talk about doing work. Work has a very specific meaning in physics. Let me go over this real quick. Let's say we have an object and we're putting a force over a distance. That's work. Work is simply a force times a distance. We write that in equation form as work equals to a force, and we put parallel. We have to be going in the same direction as the force, times our distance. And that's it. Work is measured in joules, force is measured in newtons, and distance is in meters. So I'll put above the equations what the units are. So I can have joules for work, and then I can have newtons for force and meters for distance. So a newton meter is equal to a joule. Let's do a quick problem here. Let's say that I had a mass right here, and it's 1 kilogram. So I have a kilogram of mass, and I'm going to end up putting a newton worth of force over some distance. Let's call it a meter. I won't do it to scale. But I have 1 kilogram now over here, and let's say that it's moved 1 meter. So it's maybe in space, whatever it might happen to be. I can say from here over to here, this distance from there to there, I'll just say that distance that it moved is equal to 1 meter. And maybe I'm putting 1 newton of force on this. So I'll draw an arrow straight out, and I'll say force equals 1 newton. And I had this the entire time. Force equals 1 newton. During that time, I have done work. The force is in the same direction as the distance. I've done work. Now, maybe there's friction slowing me down, or maybe this is accelerating. Whatever the case, all we need to do is multiply these together. I could say our work equals our force parallel times our distance. Here, our work is equal to, we just said 1 newton of force times 1 meter, a newton meter. We could say the work done is 1 joule. So that's 1 joule of work that we've done by pushing this object. Whatever consequences come of that, we aren't that concerned about. So we're going to use this idea with pulleys. What I'd like our students to figure out is, if I have pulleys and I have them set up in different configurations, how much work will it take for us to lift some kind of mass a distance? And we'll always lift this mass the same distance. For this table here, and I actually have nice rods that fit in here, maybe we could lift it 20 centimeters every time. And these happen to be 500 gram masses. So that's what I'd like students to do. I'd like them to figure out how to figure out work done by them. So what force are they putting on this contraption once I build them? And we certainly already know the mass, so we can find the weight. So what is the work that the students do? Now keep in mind, pulleys are wonderful in that we always are going to end up having a distance that works in our favor, because this is just a really large pulley. It's actually a wheelbarrow wheel, and I took the tire off it, and it acts just like one of our pulleys. I could put a large rope on here, and you can see all it's doing is changing the direction. And it doesn't really matter what direction that I'm pulling. I can go any direction I'd like. It just changes direction for me. So that's the beauty of pulleys. So we'll use that as a fact that we can help us as we set these up. Pulleys simply change direction. So now I have a pulley contraption set up here. I've got 3 pulleys on top and 3 pulleys on bottom. And I have that 500 gram mass hanging here. Now I have another pulley down here. And that's just so that I don't have to pull down, I can pull up. Because we're going to need to end up using spring scales. And spring scales, often called Newton scales, have a spring in the back. I don't know if you could see those, but they're a spring. It'd be worth going over with your students how this works. Springs are fascinating and just as intriguing as pulleys. But when I take a spring scale, and if I had a 500 gram mass, I can end up finding out how much gravity is pulling on it. We call that weight. And I can simply read right off here. To help get your students in the spirit of collecting data and making sense of it, we might want to run a quick experiment together. Let me just say, if I put a spring scale, by the way, this one goes to 5, this one goes to 20 newtons. In other words, the spring size in the back is a little bit different. This one's more robust. I'll use the 20. if I were to put 500 grams on here, we should read about 4.9 newtons. And we do. And the reason for that, let me just draw a quick little example here. Say I had a .5 kilograms here. Gravity's pulling down on that. We would end up saying it has weight, and weight equals mass times gravity. Weight equals 0.5 kilograms times 9.8 meters per second squared. That's what we accept gravity as. And our weight would be 4.9 newtons. Now, if you know Newton's laws, we know if it's pulling down with 500 grams, 4.9 newtons, I better be pulling up with 4.9 newtons. If not, it's going to start moving down. But if I were to take this same scale here, and I were to, let's see if I can attach another 500 gram on the bottom. Now I have 9.8 newtons. Borrow this one for a second. Hopefully it won't unwind on us. See if I can put this on here. Get a third. Put this one on here, like this. And see if I can put this on here like this. Now I've got 4.9, another 4.9, another 4.9. So I think that's 14.7 together. What I want you to notice that on our scale up here, it's going to increment down the same amount of distance each time. And that's the beauty of springs. Springs follow this linear pattern. We take these back off, get them out of the way, and then I'll draw on the board. Put that back on here. Let's make a little table. What we found is, as I put more mass on here, technically it's weight, my spring would stretch more and more. And it does this in a linear fashion. For instance, in this case, I put more and more mass on here. So for right now, we'll use mass, but technically we should probably use our number of newtons. I could say, in this axis here, and in this axis, let's say that I manipulated how much mass I put on there. So at first I put on 500, and then 1,000, and then 1,500. So at first 500 grams, and then I put 1,000 grams, and then 1,500 grams. Again, technically these are going to need gravity to work, and these would be a weight. But just to help our students think through this. We then found I got a certain number of newtons. Let me put these on here. I'll start with 0, go here, and I'll go here. We'll call it 5 here, and then we'll have 10, and then we'll have 15. And this is going to be force in newtons, and this will end up being our mass. For right now, we'll just put mass in grams. We're just trying to get our relationship. We know that 500 grams gave us 4.9 newtons. So I'll put it right below the 5 right there. And then the 1,000 gave us about 9.8, about there. And our 1,500 grams gave us 14.7, something like that. I think you can see if we didn't have any mass on there. But right away, we can see what kind of function we have here. It's going to be a nice linear relationship, a nice straight line here. So maybe I'll put it right underneath my dots here so I don't go through my dots. Just to help us kind of see what's going on there. We have a nice linear relationship. And that's why spring scales work so effectively. All they do is they use the gradient and they just increment the spaces equally. Often, we'll write this a different way. Normally, we'll end up saying, let me redraw this quickly. I'll do a smaller version. Normally, we'll say our force in newtons is going to vary directly proportionally with our distance and I can put that in meters. Now, I can stretch this to the side just as easily as I could stretch it up and down, and I'll show you why I might want to do it in the X direction here. If I put a certain amount of force, if I double that force, triple that force, we'll end up with that nice relationship again. Just kind of draw that in here. Okay, we end up with a nice X direction of displacement, and this is going to end up being a linear relationship. Y equals our mx plus b. We end up knowing that our b is 0 here, so we'll just say our y equals our mx. In this case, this relationship of force versus our distance on a spring, we call that Hooke's law. And we write it as F equals kx. Here, the x is thinking about distance in an x direction, and then that k would be our spring constant. And we already showed you that we had two different springs. The 500 Newton scale has a very small spring, where this larger spring scale has a much thicker spring. We're going to use that because we're going to end up asking students, if I always raise this mass a certain distance, and we said 20 centimeters. In other words, I always want to raise wherever the mass was, this black mass, because I'm going to set up different configurations. Wherever it starts, I want to raise it from here up to where the bottom of the weight would be here. I want to lift this the same amount every time. This is what you're going to give to the students. Now, the students can use whatever spring scale they would like, and they can end up pulling this off here. I just have this. If you take the tension off the strings here, these tend to unwind. I'll have to show you how to put these together. Like right there, sometimes they'll fall off. You'll get really good at putting these back on. But what students can do is they can use their spring scale, they can put it on here like so, and then they can end up taking a reading of the force. They can even put it on here if they'd like. But then they're going to end up pulling this until they've raised it up 20 centimeters. Then they have to calculate the amount of work that they've done. And notice, I have to do work when I'm lifting this up. So I'll put this back on here. Now, students are going to be very excited about working with pulleys. There's no doubt about that. What you need to do is simply ask them to make a claim and try to back that claim with data and evidence. And that is going to help us get through this lab. I need to set up a couple other sets of pulleys. I have a 3 and a 3. Maybe I'll set up a 2 and a 2 and a 1 and a 1. You need to decide as a teacher how long you want to take with any of these laboratory experiences. For instance, do you allow the students to try to set these pulley systems up? Turns out they're really difficult to do. That 3x3 that we were showing you earlier, that might take your students an hour to set up. It's really challenging. They keep falling off, they tangle. If it doesn't work out perfect, it's often better just to start back over. Your students might not learn that lesson. So you need to decide, do you want your students to go through that? And if the answer is yes, then it's obviously going to meet one of your objectives. But usually that is not where you want them to end up spending all of their time. You might want to set these up for them, or give them a simple one to set up. And I think they'll get the idea, oh, this takes a little bit of skill. But that's not the skill of a scientist. Scientists aren't really about setting things up in mass, right? We really want the minds on instead of just hands-on. And this is where a lot of times laboratory experiences become this hands-on idea that if students have their hands on something, they're learning. Not necessarily. So you have to really think through what you'd like. So I'm going to end up setting this up for them. But if you do have them set up, you still want to figure out ways of allowing them to express their ingenuity. In other words, are there better or worse ways of setting these up? And I can tell you from experience, there are. Sometimes it's easier to tape them together so they can't fall off while you're winding them, and then you can take the tape off. If you're going to do that, make sure that you're making a point of that and point out the ideas that are much more fruitful versus just a grunt method. So I'm going to set these up I'm going to use a 2x2 and then a 1x1. I'm going to go in detail on how to set up a 2x2 pulley, and if you're not interested, just skip ahead. But part of the reason of making this video series is to encourage students and teachers to engage in experimentalism in the classroom. It really depends on the teacher. And if the teacher doesn't have the time to figure all this out on their own, maybe that's something that we can offer here. So in this situation, I'm going to use a 2 set of pulley up top here. So in other words, just a pulley next to the other, and they move independently of one another. You'll notice that pulleys will have a hook going either parallel or anti-parallel, and you want to figure out which direction you'd like. These do not fit around the bolt that's going into that clamp, so I use zip ties. You could use string, anything you'd like. Just something that's strong enough I can slip this on here, and in this case, I'm going to put my pulley where the hook is parallel with the other set. I have another one that's going to end up being down here. Now I need another set of direction changers, so this pulley here, and that attaches right to this cart. I'll put this down here. I want to make it similar to the other pulley, and then I'll use string. Now, how much string do you use? Well, that's hard to know. But here's a hint. Once you do a laboratory experience like this, try to do it every year. You'll get better and better. What I encourage you to do to save yourself some time is, once you have a 3x3 set up, and maybe you will use the same room or closet or table, demonstration table, whatever it might happen to be, put these, wrap them around, put a little piece of tape on them so they don't unwind, and write 3x3 or 6 total pulleys, however you want to remember it. Put that in a Ziploc bag, put it in a drawer so you can take it out next year, and you'll already be that much further ahead. You've already found your pulleys, whatever equipment that you're going to use. So think of everything that you do as an investment to make your life easier in the future. All right, so the first thing that I need to do is I need to put some kind of loop. In the end, I need to have a holder for my rope up top here. So when I'm done winding everything, I can end up hooking it on here. I will tell you this, if I were to take all of the weight off of here and let this sit, these will often act like springs and just pop off, and it's going to end up as a knotted mess. I always use this particular knot. I just fold over a piece of rope like this and then treat it as one piece, tie a knot. I have a nice loop on here, and if I don't want, oh, I just lost my scissors. So pause for a sec. Back. If I don't want this extra, I'll just cut that off. I'm going to put this up on one of these clamps. Like this. Now I can start unwinding my string. How much do you need? Well, that's to be determined. So maybe what I'll do is I will follow my first pulley system, and in this case, I'm going to unwind a bunch of this string, and then I'll hook it on last. I think that might be easier. So I'll take this, and just like on this one, I'm going to start on one side and work my way over. So I'll start the same side. If you already have a knot, you can end up putting it through here. Often it won't fit between the pulley groove and the top, so I like to go through in between the pulleys. And I can pull that through, see if I have enough, and then I'll take the other pulley on bottom and I'll just start sending it through however I'd like. It doesn't really matter, just get it through there. Now you want to try and put a mass on there. and that mass is going to supply you some tension. Or maybe I can go one more loop. This is just a 2x2, so I'll take this over here like this. I have to put them in between the pulleys. This is easier said than done. This gets a little bit tricky. So I've got to flip this one over. So I'll put this pulley on. I'll put this pulley on. Here's a good technique. Take your two fingers and kind of split them. Now, let's try this again. And then I'll just slip it over that pulley right there. And I'll slip this one over this set of pulleys right here. And then I'm going to come back through. I'm going to hook this on to my weight. I already felt one pop off. So pull down on this. See, easier said than done. What I need to do is I need to tie off my pulley. And in order to do this, I'm going to get a rough length. So I'm going to send this back through, and then I'll put all of the pulleys back on. But if if you think that you're going to do this quickly, you're probably wrong. So let me put this on here. I can get my rough amount of distance that I need, or I should say length. So that looks pretty good. So I've got roughly about that much string. I'm going to cut off a little extra. I can always take the extra off, but I can't add as easily. So it's going to want to wind on me. I'm just going to put a loop at the top. I can always make another loop, but you got to keep that tension on. I'll put that loop right on here. Now what I can do is I can start tracing back. I'll take it goes up, this first set. I'll put this on here. That side is on, and then that side is on, so hopefully if I put this side on, they're not tangled. Notice I'm still pulling on it to leave tension on there, and I'll put this one up here. Now, oh boy, let's see here what happened. One got tangled up here, so if it's not too bad, you should be able to salvage it. If not, as I said before, sometimes it's easier just to start back over. So this comes up, this one goes down. Oh, I strung it wrong, so I flipped it, and what I'm going to do is I'm just going to restring it. But it's really not going to take that long now that I have this. It rotated on me without me noticing, so I'll just take this bottom one and hook this over here. Good. Now, this one goes up, down to this side. So anyone who thinks that they're going to be able to do this easily, let them try. It's much harder than you think. Leave the mass on here. Now I can end up sending this through towards me. Just take your time. Try not to get frustrated. And then up here. All right. You know you've done it correctly if you don't see anything crossing over. Now I'm wearing the wrong glasses. I actually need glasses that'll magnify a little bit more to see really what I'm doing. But this should now move freely, and it does. So I'm going to work on the next one. All right, I have my 3 on top, 3 on bottom, 2 on top, 2 on bottom, 1 on top, 1 on bottom. You'll notice that I don't have them completely even in terms of their starting position. As a teacher, decide, do you want to fix this for the students, or do you want to let them figure this out? Another thing as a teacher that you can do, and really what you want to avoid more than anything, is having these unwind during class. And if you have a separate table for each one of these, great. If you don't, put them all on the same table. Maybe the other side of the table. You can get, 2 sets of 3, however you can do it. The big point here is that whatever you have, make it work. and you'll get better and better. But just don't get discouraged. And if it doesn't work out perfect the first time, it will get better and better each time that you try this. Let me show you a little trick. So that this doesn't accidentally unwind, I can also take, and notice this one's already at the ground, I can take this rope right here and I can put another loop right in it, right in the middle of the rope. I just fold them together as if they're one, and then I just make a little knot, just like I showed you before. Give myself enough slack, and I can put this right back through itself, and I can make a loop right in the middle of my rope. That way, when students are using their spring scale, they don't ever have to take it off there. So if they ever let it go, I'll always have a safety. Just something to consider. Now that we have this set up, again, I've just set up the 3 here in the interest of time. Now challenge your students. Have them make a claim and back it. In other words, you've already told them, I want each one of these to be lifted. The black mass here, this 500-gram mass, here, here, here. They're all the same. I want those to be lifted 20 centimeters as they're pulling it, and I want the students to tell how much work they've done and compare them. That's what we want them to do. So you might want to give your students a few minutes to think of a claim. Now you might be thinking, why are you having students make claims when you've already told them what to do? Well, first of all, no matter what you tell them to do, as soon as they start getting to collect data with pulleys, they're going to be very excited. They're going to have an awful lot of fun. And whatever you wanted them to do, it's probably not going to happen. You could write out steps for them, but I encourage you not to do that. This is all part of it. Simple claims are what we're trying to do in science. You're saying, I think I know the answer. And by the way, students are going to think they know the answers to all this. Remember, as I mentioned earlier, a lot of students think that pulleys are magic and they can allow you to do things that you couldn't do otherwise in a magical form. And it's not magic. So they're going to end up brainstorming. Now, you can allow them to start interacting with those pulleys now, or you can force them to end up writing down their ideas. It's really important that they write it down. Students will, after the fact, say, no, I thought that the entire time. Turns out they didn't. In hindsight, they think they will have, but no, it's not true. So have them express their ideas as cleanly and clearly as possible before you allow them to go to data collection. Now, data collection is going to be what they love. They associate doing real science as whenever they collect data. They're going to feel as if they're a scientist. Look, I'm doing something and I write something down. But you'll find out very quickly that students often have no idea what they're writing down or why they're collecting it. So quite honestly, data collection is kind of a low-level skill. And I use the word skill because that's about all it is, if that, right? So data collection is not something that we're really after. It is something that is necessary to achieve higher end goals. Regardless, if your students are working together, either at their tables, at their seats, individually, with a group, however you'd like to run this as a teacher is absolutely fine. But they should be brainstorming about this. And if students have been through some of these experiences before, as one student makes a claim, the other's going to instantly be skeptical and question them. If they haven't done anything like this before, they'll probably blindly accept and say, that sounds like a great idea. I bet you that's true. Regardless, you might want to consider how you're assessing your students. This is how I do it. And up here I have BS for brainstorming, not the other kind of BS. I want students to be brainstorming, and I want them to CP, claim positing. I want them to posit a claim. Remember, that lets them know where they should be going with their experience. If they don't make claims, they will just spend all of their time collecting data, writing down everything they possibly can. They'll say, well, I have a blue pulley and it's on the left and the orange string and it has a interesting texture and the bars are so, they'll just write everything down. It might have nothing to do with anything. But again, They think that observations and writing things down, that's what makes science. And it's not. What makes science? That argumentation, making and backing claims using data and evidence. So, what might be a claim that students would have? On this particular experiment, they might have a low-level claim. They might simply say, as I pull on the string, the mass will go up. That's very, very low level. But at least it's something. You want to get to higher and higher domain type of claims. And we'll see that in a bit.